Well, good. Well, good. All right, let's get started. Happy Valentine's Day, everybody. I put a couple hearts on the announcement slide just because it's Valentine's Day.
My love is not unconditional, it's biconditional. I love X if and only X is you.
Sorry, I had to process that one for a little bit. Okay, all right. Let's get started. I've got the sign-in sheet going around. A couple things. So remember that homework 4 is due next Wednesday. I'm going to pull some things up and show you all some things about it. So it's due Wednesday on the 21st. Remember, I'm not accepting late submissions for that homework because the moment you turn it in, no pun intended, online, the solution is going to be turned on because the exam is Friday, February 23rd. So that way you all will have the homework solution ready. Don't forget, Engineering Career Day is next week, and we could use all the help that we could get for the morning activity. So please come on by. A lot of potential employers might be there as well. Nudge, nudge, wink, wink. So that's worth mentioning. Yes. It's the event goes from about 9 to about like 1-ish. The high school students will be filtering in from like 8 to 9. Like that's like when the buses are coming in. So if you're here around 7:30, 7:45-ish to help them get set up, man, that would be great. And if you're interested, let me know. I'll like get some. If I get a list or get. I tell you what, if the sign-in sheet's going around and you haven't gotten it yet, go ahead and like put your name there down. And if you're interested, just and you didn't get a chance to put your name on the sign-in sheet, just tell me after class and we'll get you down. But yeah, we'll talk about it a little more after class. Everybody good on that? Yes, we are still having class on Career Day, which wouldn't be that big. It shouldn't be that big of a deal because at that time all the exhibits will be going on. So really, we'll just need a few folks to escort some students around. And if it's not you all, we can probably find some other students so we can tag team that. That shouldn't be that big of a deal.
Who's putting this on?
The SAME Huntington Post is organizing it, but a little bit of them, a little bit of us, a little bit of some private companies. So it's a big to-do.
There's going to be kids there too, right?
Yes, high school sophomores, about 150 of them. So yeah, quite a few. Like the surrounding area, there's I think like 15 different high schools. So sound good? Okay. I said I would mention a couple things about homework 4, so I thought I would pull this up. One of the things about homework 4, for instance, is that there's a lot of sort of supplemental instructions. So, for instance, on problem number 1, you're going to do textbook problem 413. There's a couple points to go along with that. So the live loads that are indicated in the problem are already reduced. You don't have to worry about live load reduction. Now, this second bullet's kind of important, okay? For your design, assume a D over B ratio of 2 and a height of the beam of D plus 3 inches. Now, because of that, whatever design you get is not going to match what's in the textbook. The textbook has a design, and it's not going to match. So everybody, you're raising, well, I didn't get what's on the problem. Well, that's why, okay? Because that's sort of on purpose. These two, just make sure you compute your efficiency and determine whether or not the beam meets your ACI limits on strain and reinforcement. No big deal. That's basically what you did on homework 3. That's sort of the point of homework 3, so that wouldn't hit you like a bucket of water. And then the last one, this is a hint. I talked about this in the last example on the slab. Compute the dead load moment and the live load moment separately, then do your 1.2 plus 1.6 live to get the factored moment. Don't try and get a factored load and then do WL squared over 8. That's not correct. That won't work. So that's sort of my hint on that. On problem 2, now on problem 2, what I did on problem 2 is I actually gave you the dimensions of the beams. The idea on problem 1 is an unknown cross-section. Problem 2 is a known cross-section. So you have the dimensions. The live loads are already reduced. There's a statement there about rho. Disregard that. Disregard the statement regarding rho. Compute your efficiency and ACI limits, and the same hint on the moments. And then problem 3 is simple. That's just a slab problem. So, and then the live loads on that slab problem are already reduced. Just 3 problems, yes. Just 3 problems.
Scroll down a little bit more. Is there more? I mean, it's 11 pages.
That's the solution. Yeah. I could, yeah. I don't love you that much. But nice try. Okay, so everybody good so far? Any questions? Don't forget that's due next Wednesday. Okay, so today what we're doing, just so everybody's aware, okay, we are starting material that is not going to be on exam 2. However, 2 things. One, I don't want you to think it's unrelated to exam 1 material, because it is kind of related. Up until now, a lot of our analysis and design procedures have been focused on rectangular beams, just a rectangle, okay? And what we're going to be doing now is assessing beams that are of a different cross-section. So it's not like the underlying design principles and mechanics are any different, because they're not. I mean, it's still 0.85 FC prime, it's still same strain limits and all of that. That's all the same. The only thing that's different is the geometry of the beam. So I know it can be sometimes tempting to go, oh, this is exam 2 material, let's just not pay attention. Well, it actually, no pun intended, will serve to reinforce what you're learning on the material on exam 1. I swear I didn't mean for that to come out funny, but it came out a little funnier than I thought. And point two, I will go ahead and tell you this. This might surprise you. I told you this isn't exam 1 material. It's actually not even exam 2 material, okay? I'm not going to put flanged sections on exam 2. I'm not going to put doubly reinforced sections on exam 2 either. I am going to give you one beefy homework assignment on it, though. But the upside is that you don't have to do it on the exam, because while this is incredibly important material, it is still just more beam stuff, and since exam 1 is basically on moment and on beams, I feel it's not really, why test you again? So just to be aware of that. Okay, let's get started into it. Let's talk about this. So we're talking about flanged sections, and basically what I'm talking about are either T-beams or L-beams. Not really much of a difference on either one. We're basically going to focus on T-beams in here. There's a real difference because they present the same geometric challenge, okay? Now, what I'm talking about is this. I mean, when you're typically looking at cast in place or even a lot of precast reinforced concrete systems, you know, up until now, let me turn this off. Sorry about that. Okay, up until now, we've been treating the beam and the slab as if they're completely separate units. And that's not really true in a lot of cases. A lot of times what happens is, whether or not you're talking about a precast system or a cast-in-place system, they're sort of cast monolithically. In other words, you know, you've got, let's say, some formwork, and when you pour that, you're not pouring the beam and then pouring the slab. You're pouring it all together, so it's one continuous unit. So looking at this as if it's a rectangular beam is not really the most accurate in a lot of cases. Really what you need to do is you need to look at this as if it's a T-beam, okay? A beam and then a portion of the slab acting as your flexural element. So a couple things on terminology. If you recall, that flat portion that's on the top or on the bottom, you know, if it was an I-beam, we call that upper flat portion the flange. And then the bottom portion, we call that the middle portion, we call that the web. Y'all remember that terminology before. So this is where some of that notation, that terminology that we introduced a while back, but we really haven't seen it pop up very much. Now it's going to start to pop up. For instance, there's now some new definitions in regards to B. So B sub W is the width of the web, and that's the width of this smaller sort of stem portion on the bottom of the cross-section. The upper component, B, that's what we're determining the width of the flange. And I have here effective flange width, and I'm going to sort of describe that here in a quick second. Everybody with me so far? Okay, so imagine, let's take a look at this first. Let's say I've got a floor system like this, and let's say it goes on forever, and I've got beams spaced, I don't know, every 10 feet, so on and so forth, and they go on forever, okay? One of the big questions that we have to ask in regards to T-beams, and this would be the, what? Now, that's astronomy, that's physics.
It goes on forever.
Okay. My goodness. Goes on forever. Okay, it goes on for about 500 feet, all right? There we go. We're not going to hit Mars going that way. Okay, all right. But one of the questions that we have to ask is this. So let's come up with some dimensions. Let's say that it's 10 foot from center to center of beam, okay? Now let's go back to some earlier material. Do you all remember the concept of tributary area, right? Tributary area is basically stating how much this beam is responsible for. And what we said with tributary area is that this beam is responsible for halfway over to this beam and halfway over to that beam. So if the beam spacing is 10 feet, that means the tributary width is also 10 feet, right? Because it's 5 feet on one side, 5 feet on another, right? Now that's looking at it from the load standpoint. In other words, how much load is that beam responsible for? But now I'm sort of asking a different question. Now what I'm asking is, if I have this beam and I have this beam and slab system cast together, how much of that slab can I count on to be effective for that beam from a resistance standpoint? Is it the tributary width? Maybe it's a little less. Maybe it's a little different. Okay? What I'm talking about is a concept called effective flange width. In other words, how much of that slab can we consider to be effective in transferring load to that beam? Sometimes it's the tributary width, sometimes it's a bit less. If you actually investigate the bending stresses in a beam and slab system, what you find is, okay, so here's the beam, sort of going along like this. What you find is that if you start measuring the stresses farther and farther away from the beam, the stresses, they sort of decrease. They get smaller and smaller and smaller, and they sort of start to dissipate. So the idea is this green curve sort of quote-unquote represents what's really going on, and the idea is, well, can we idealize that as an isolated chunk of that flange? And that's what we're talking about in terms of effective flange width. Does that idea make sense? Now, let's be clear. What we are talking about is a very complex analytical challenge. It's not simple. It's not something that I can just write a differential equation for and solve for x. This is 3D. We're talking about different material behavior. We're talking about transfer of stresses longitudinally and transversely. This is not easy to determine, okay? And as you are aware by now, we as engineers, we sometimes encounter a situation where we've got really complicated problems, but unfortunately, we got to have an answer for them, okay? And that's where an empirical relationship comes into play. So you all have already used empirical relationships in here, the whole square root of FC prime that shows up from time to time. Even 0.85 FC prime is an empirical relationship. You all have probably seen empirical relationships in other classes like hydraulics or transportation or something like that. This is another empirical relationship, okay? So what this expression will tell you is it will tell you the effective flange width for a given beam based on the following criteria. Now, first off, I've got T-beams and L-beams. Really, the only difference between a T-beam and an L-beam is this. Remember how I said let's idealize that the floor system goes on forever? Well, in reality, it doesn't, okay? And in reality, what it's going to do is it's going to do something like this. So it's going to go on like this, and go on like this, and so on and so forth. So this internal segment right here, this might be what we call a T-beam, because it looks like a T. What we're talking about in terms of an L-beam, we're really talking about the beams on the outside, okay? But the actual analysis challenge and the actual calculating phi m in and the design, it really doesn't change. The only thing that changes really is this. The way that you compute your effective flange width is a little different. So these are two expressions to help you determine how much of that slab you can consider effective in transferring load to the beam. And we're primarily going to look at T-beams. Again, no difference. That's just a different expression for T-beams versus L-beams. But we basically calculate three quantities: the span length divided by 4, the beam spacing itself, and then BW plus 16 times the flange height. We take the minimum of those, and then the minimum of that value, whatever that minimum is, that is what our effective flange width, this term right here, that would be this dimension, this term B, that would be the dimension that we would consider for our analysis. Does that make sense? Yes.
Is it S, the beam spacing, not rebar spacing?
The beam spacing, yes, yes. So this is S. That's S. So far, so good? Okay. Now, there's another little challenge that pops up in T-beam analysis, and that's this. Okay, I'm going to throw out two terms at you that are going to seem really strange. I'm going to throw out the term rectangular T-beam, and I'm going to throw out the term true T-beam. Okay? Here's what I mean by that. Okay? Let's look at this from an analysis standpoint. Okay? Let's say we're trying to determine MN, nominal moment capacity, or phi-MN, design moment capacity. It doesn't matter, either one. But what's the first step in either one of those computations? Well, it all starts with equilibrium, right? It's the same thing with a rectangular beam or the triangular beam that you did on that last homework assignment. It's no different. I have some tensile force, right? So the tensile force is the area of steel times Fy, and then that has to be matched by some compressive force. And the compressive force is something like 0.85 Fc prime times whatever area is in compression. Make sense? And so then what you would do is you would take that relationship and you would determine, well, what we did before is we determined A. We said, how deep does that stress block need to be such that C equals T, right? But really, in general, what we were generally determining is how big does that stress block need to be? What's the area of that stress block? Well, how big does it need to be such that compression equals tension? Make sense? Now, dependent upon your dimensions and dependent upon the proportions, the area of the steel, etc., you could wind up with one of these two scenarios. Now, the scenario on the bottom has a stress block. This is a stress block such that C equals T, and the stress block actually looks like a T. It actually has a T shape to it. Okay, this is what we would call a true T-beam. Okay. We call it a true T-beam because its stress block is T-shaped, but the one up top is a little different, okay? While the beam is physically a T-beam, its stress block isn't. Its stress block is just a little rectangle, right? This is a rectangular T-beam, and what makes this interesting is how would you compute the flexural capacity of this? Well, it's just ASFYD minus A over 2, because how is this any different from just the rectangular beams that we did before? You had a lump of steel and a rectangular stress block. That's the exact same thing that we had before. So does that make sense? One of the things we're going to have to do in a T-beam analysis is actually figure out which one we're dealing with. So that'll be sort of an added complication with what we're talking about. And don't worry, we got a few different examples looking at this. We've got two examples looking at different T-beam scenarios. What I want to do for this, we're in analysis phase. We're not in design phase. Okay, bless you. What I want to do is I want to compute the flexural capacity of this beam. So I'm really looking at this from a nominal moment capacity. I just want to stop this at phi-MN. Okay, so I've got a beam. Now let's make sure we're clear on the terminology. Okay, so D is 24 inches. That is from the top of the cross section to the center of the steel. Okay? So it goes from the top down to the center of the steel. Okay. Now, let's see, what else do we have? So H sub F. I don't think we've dealt with this one directly yet. H sub F is the thickness of that flange. Okay, and the thickness of that flange is 4 inches. Okay. Now, excuse me. Now, We have an area of steel. It's actually in 2 layers. That's actually not really going to matter for our purposes and what we do, but you're going to see how that isn't going to matter here in a second. So we have 6 number 9. So you remember a number 9 is 1 square inch. This is pretty easy. And now let's make sure we're clear on the difference in the B's. B is the effective flange width. We don't know what that is yet because we have to look at our floor system. B sub W is the width of our web, or that stem on the bottom, and that's 10 inches. Make sense? Now, a couple other things. This beam is 30 foot long, and we're going to say that the clear distance between the webs is 50 inches. And I think you'll see where that comes in here in a second. Everybody got this so far? Don't worry, I'm going to draw a lot of this out. Okay. Don't worry, a lot of this is going to get repeated. All right. Okay. So this is going to test my 3D art skills a little bit, but we'll make it work. All right. So actually, I don't like that. All right, so okay. All right. Okay, so here's our floor system. Let's get a couple dimensions on here. So this dimension here is H sub F, and that is 4 inches. And then this dimension here to where the center of the rebar is D, and that is 24 inches. Now, this system has sort of 6 bars, sort of looks like that, and they sort of go along the beam. And ultimately what we're trying to determine for a given beam is what is that effective flange width, or at least that's what we're trying to determine right now. So, about like that. And so we're trying to determine B is trying to determine that dimension right there. Okay. Now, let's be clear on something, okay? The problem gave us a few things. It told us that the span length was 30 feet, which we'll need that here in a second. It told us that the web width was what? What was BW? 10 inches. But then what was the other dimension it gave us? It said the clear spacing between the webs. 50 inches. Now, clear spacing between the webs, what we're talking about is literally from face of web to face of web. In other words, if I went out there with a tape measure, what can I measure easily? It's from here to here. Measure that out. Okay? So help me out. What is the actual beam spacing, the center to center of the beams? It's 60 inches, right? Because it's 50 and then half a web on each side. So from here to here, S, and let me do this. When I write my S's, I put a little, I put a little tick mark on there so that I don't confuse it with 5s. All right. Does that make sense? Okay, all right. Now, We need to determine what that B value is, and it is computed as the minimum of L over 4 BW plus 16 HF, and then S. And then again, I like to put myself a little tick mark on there so that I know that's not a 5. Now watch this, okay? Let's do the middle one first. So that's 10 inches plus 16 times what? 4 inches. Okay, let's do the bottom one. What's the beam spacing? 60. Now what do I do on the top one? So it's 30 feet, so we got to convert. So 30 feet times 12 inches per foot divided by 4. So does that make sense? Well, it depends on your dimensions. So you could have, that's a good question, and it just sort of depends on your dimensions. What's that?
When your S change, your B changes, it's basically the same thing.
I don't get, I'm
Like, how would it ever be anything but S? Because it's basically the same dimension, just...
well, hold on, just bear with me. Let's do some number crunching, all right? What are we getting for each of these values? 90, 74, and 60, okay? All right, what happens if your flange height changes to like 3 inches? So that would govern.
But how does that, wouldn't that change your S if it did? It's basically the same dimension.
No. The height of the no, we're talking about there's a difference between B and BW, okay? There's a difference there. All right? What I'm saying is this. Your height of your flange is 4 inches. Change that to 3 inches, and this governs.
I'm saying if your B changes, your B gets longer or shorter, then your S is going to change.
No. You're making the assumption that B is always half and half, and it's not. It's not the same thing as tributary area. That's the whole point. If it was tributary area, we wouldn't do this, okay? Tributary area is asking how much is that beam responsible for, and that is always S. What I am now asking with effective flange width is I'm asking how much of that slab can I count on for resistance, and that is not always the tributary width. That's this, okay? What I'm saying is, you know, so it isn't always S. I mean, like I said, here's my example. What if your HF was 3 inches? If your HF was 3 inches, S wouldn't govern. It would be the center one.
I understand the calculation. So now the slab, like the B equal overlap.
No, that's a great question. They'll never overlap because S is always a minimum. Yes, exactly right. It's not a matter from a load standpoint. I'm not saying that the beam isn't responsible for the weight. I'm saying it doesn't count for that beam's capacity. That's what I'm saying. But yes, there can be a no man's land, as you're saying. No. That's a great point, but that's not what I said. Let's also remember we did slab design and we placed reinforcement this way. So it's not like the slab is just hanging out in space and it's not reinforced at all. Okay? Don't confuse that. Okay? Remember, there is a difference between how much that beam has to hold up from a load standpoint and how much of that slab we can count on to help that beam hold up that load. Not the same thing. Okay? Does that make sense? Now, it just so happened to be the same for this example. Not always the same. Does that make sense? Okay. All right. Now, The next step that we have to do is we have to make an assessment as to whether or not this is a rectangular T-beam, whether this is a true T-beam, okay? So let me show you how I'm going to do that, okay? So we're going to determine the location of the neutral axis. Okay. Now we're going to do that based on the principle that C equals T. Okay? Now, help me out with this. What is the tensile force in a given beam? Just ASFY. Okay? Now, regardless of the geometry, ignore the geometry, how do we generally determine what's the compressive force? Generally. Point of your stress block, right? So 0.85 FC prime times whatever area and compression is required. So let's just write that out. So 0.85 FC prime times the area of your stress block, we'll call it the area and compression, has got to equal ASFY. So let's solve for how much stress block we need in order to maintain equilibrium. So the area and compression has got to equal ASFY divided by 0.85 FC prime. So that is, what's the area of steel? So 6 square inches times 60 KSI divided by 0.85 times 4 KSI. So what does that come out to be? Say it again. Square inches? It's an area, right? Okay. All right. Now, over here, I want to calculate the area of the flange. Okay? And I propose that the area of that flange is just that rectangular portion on top of the beam. It's just B HF. So what does that come out to be? It's 60 inches times 4 inches, which is what? 240? Okay, so I'm just curious. Based on these numbers, it's a rectangular T-beam, right? It's not a true T-beam, okay? The reason why is this, okay? Here's your beam. Okay? And what we did, this area of this flange, we sort of drew a dashed line, and we said, all right, we drew a dashed line, and the area of this box up here is like 240 square inches. But we only need 105.88 square inches in order to maintain equilibrium. So what we've got is a stress block that looks something about like this. So the area of the whole thing is 240. The area of the stress block is only 105. Therefore, we've got a rectangular T-beam.
I'm still confused on what's the difference between a true and rectangular.
Okay.
Basically, if it was over 240, then it'd be a T, right?
It's going to be a little clearer after the next example, but just bear with me on this explanation. Do you agree that the area of the top of that flange is about 240 square inches? All right. Would you agree that the amount of compressive stress block we need is about 106 or something like that? So we can fit that stress block up here, right? So the stress block, what does it look like? It's a rectangle, right? So this is a rectangular T-beam. Now, let's say that this came out to be like 320. If this came out to be something like 320, then our stress block would have to fill all of this and then some going down. So the stress block would actually look like a big T, right? In that instance, we'd be dealing with a true T-beam. So the difference between rectangular and true is not the shape of the beam, but the shape of the stress block. Does that make sense?
Yeah.
All right, you then you.
So can we like generalize any shape and say the first term, like for our nomenclature, is going to be shape of the stress block, shape of the overall stress. So it'd be like rectangular, whatever the shape is.
What I am ultimately trying to do in this entire process is cultivate your understanding of how we're deriving this for various cross sections. The idea is if I throw something at you like, oh, I don't know, a triangular beam, but
It's always going to be triangular.
no, but it could be a triangular beam. It could be like if you look at pre-stressed cross sections, like they're not sometimes they're not perfect T's. They've got like triangular components, and the cross sections aren't pretty. You know, or, I mean they look pretty, but geometrically you got triangles and rectangles and stuff all over the place. But the idea is that if you understand these principles, you can figure this stuff out where the neutral axis is and sum your moments and so on and so forth. But the idea is to test you by making the process harder and harder and harder. Does it?
Does the area of compression versus area of the flange, is that ever going to be the same or like very, very close?
That's a good question. Are the areas going to be the same? Let's say they are exactly the same. Is it a rectangular beam or a true T-beam? It's rectangular because it's still a rectangular stress block. So, I mean, does it happen in practice? Very rarely, but even if it did, it would just be a rectangular beam. Does that make sense?
Yeah.
Sound good? Okay. If that makes sense, I really want to focus on what this looks like. Let's look at like example 5 and example 6. What did we have? We had a lump of steel. We had a rectangular stress block. How is that any different from this? A lump of steel and a rectangular stress block. I propose that if you have a rectangular T-beam, then the calculations are as follows. A is ASFY divided by 0.85 FC prime B. Now pop quiz, which B do we use?
That would be the depth of the stress block.
No, A is the depth of the stress block. You are right, how deep that stress block is. But what B do we use? 60. We use the width of the stress block. So 0.85, 4 KSI, 60 inches, and then 6 square inches times 60 KSI. Now let's compute this and let's see if this is a number that makes sense. Without doing any calculations, using a calculator at all, would it make sense if this came out to be 2? Actually, exactly 2. Let me illuminate what I mean by that.
Yeah. Not exactly 2, because it has to be another feet under.
For the depth to be 4, like if the stress block was 4 inches deep, the area would be 240. If the stress block was 2 inches deep, it'd be 120, right? See what I mean? So what I'm saying is it's probably a little less than 2, right? Say it again. 1.76. Does that make sense? If the rectangle is 4 inches deep, it's 240 square inches. So for it to be 105.88 square inches, it's probably got to be about, oh, I don't know, 1.7 so inches, right? Does that make sense? Again, I want you to, like, I want this all to make sense. All right? Are y'all good? Y'all good? Does that make sense, though? Okay. All right. So 1.765, is that what we got? Okay. All right. So now that we've got this, we can compute our MN just like we did before. This is no different. It's just a rectangular beam. All right. So ASFY D minus A over 2. So that is 6 square inches. my decimal point is not showing up, and that's bugging me. And 60 KSI. See, 20, was it 21? 24. I swear, when this pen gets closer to this top right corner of the screen, it does not like me. 1.765 inches. It's running out of ink. That's what it... Now that was good. That was good. Now what are we getting here, and what are the units going to be? Inch kips. And what's the value? 8322.3 inch kips. And in foot kips, what does that come out to be? So we'll just keep it simple. Something like that. All right. What do we do now if we want to determine phi mn? This is a good review for the homework and the exam. Because continue that thought. But you hesitated. Why? Because you don't know whether or not it's 0.9 or not. You have to verify that. Now, how do we verify that? Where do we start? Well, so it's the strain in the steel. What I'm asking is, what is the first step to getting the strain in the steel? Beta 1 and C. So there we go. So what is beta 1 for 4 KSI concrete? 0.85. So C is A over beta 1, which is 1.765 inches divided by 0.85, which is what? Say it again.
2.076.
I have a second on that? All right. Now, what I'm going to compute is this. I'm going to compute the strain in the steel, but I'm actually, if I want to get technical about my notation, I'm computing E sub S, not E sub T, because I'm computing the strain at the center of the steel, not at that extreme layer. But it's not going to matter here in a second, and I think you'll see why. 0.003 D minus C over C, which is 0.003 24 inches minus, oh, it's right here, 2.076 divided by 2.076. And what does that come out to be? Okay. So seconded. So compare that to, first off, is that better than 0.004? A lot better. Is it better than 0.005? A lot better, yeah. So the only thing to address is, well, wait, Dr. Mike, you computed the strain at the center of the steel. What about the strain in the extreme fiber? Well, just make sure make sure you're using common sense on some of the dimensions and the specifics on what's going on. Remember, here's your steel, right? Okay. Now, what does your strain profile look like? Okay. We got that, right? We have a strain in compression, and then it goes down to a strain in tension, right? Now, if we want to get technical, what we just computed was the strain in the middle. But if I wanted to get scientific about it and compute the strain at the extreme fiber, all we're going to get is a value that's even larger, right? It had to be over 0.004 for it to be good on ACI limits, and it had to be bigger than 0.005 for our phi value to be 0.9. Well, at the center, it's 6 times what it needs to be. If we go down, it's just going to be even higher. Does that make sense? And usually on T-beams, depending upon your like especially with rectangular T-beams, you usually have no problem at all with limits like this. So I propose that phi 0.9 and phi mn is 0.9 times 693.5 foot kips, and phi MN is what?
624.
Bless you, 624.2? Do I have a second on that? What do you think? That's not bad, right? I hope it's not. Okay.
That's to the neutral axis.
Yes. So remember, A is the depth of your stress block. C is that.
So on your like the slide before this example, it has like the neutral axis and then like hash marks.
What?
Not really graphical, right? Slide.
No. Remember, you talking about this?
Yeah.
There is a difference between C, which is the depth to the neutral axis, and A, which is the depth of your stress block. Remember, there's a difference.
The hash mark is above the neutral axis. It's not.
No, what this slide is showing is the stress block.
And then it has the neutral axis label.
Oh, yeah, I guess you're right. I guess that should be lower a little bit. I see what you're saying. In this slide, it's referring to neutral axis based off compression and tension. I could see where that would be a little confusing. You're right. So, to be technical, your stress block is sort of like that, and that's going right here. But your actual neutral axis where the strain profile is a little lower.
So there's a chance that your neutral axis could be below the T where your stress.
Yes, and that doesn't affect it changing from being a rectangular T-beam to a true T-beam at all. The only thing that delineates whether or not it's a rectangular T-beam or a true T-beam is where your stress block is. That's a good question. So that's a really good point to make. But it doesn't affect your capacity check at all. So, any questions? All right. Now, for those of you that, oh goodness. For those of you that have powers of precognition, if example 9A was a rectangular T-beam, let's take a broad, wild guess as to what's going on with example 9B. It's a true T-beam. Okay. Let me sort of walk you through what's happening with this and what's going to happen for the next couple weeks. So what we've done now is we've done an assessment on how to analyze a T-beam. We're going to do another analysis on how to analyze a true T-beam. The next step is to then look at how to design a true T-beam or design a rectangular T-beam, or basically just design a T-beam. Okay, so that'll be what we do next. After that, I do want to illustrate this so everybody sees the path moving forward. After that, what we have is this. Okay. After that, we have what's called an analysis of doubly reinforced beams. And the idea is this: up until now, we've only considered reinforcement in regions of tension. That's what a singly reinforced section means, is that there's only reinforcement in the tension region. But in reality, when you're tying together your rebar cage and tying together the reinforcement, you generally have a little bit of reinforcement in compression anyways, okay? So the last thing that we do with beams, with beam analysis, with moments, is how do you analyze the capacity of a beam that is doubly reinforced? I'm not going to lie, that it actually gets a little interesting because you have to actually check and determine whether or not that compression steel even yields or not. Sometimes it does, sometimes it doesn't. So the tensile steel, it always has to yield. But the compression steel, it can, and sometimes it does and sometimes it doesn't. There's no requirement that says the compression steel has to yield. And if it doesn't yield, the analysis gets a little trickier. Okay, so it's kind of nifty, but I think it's worthwhile to do. We don't really design a doubly reinforced beam, but we do need to understand that math in order to understand how beam columns work later. After that, we get into exam 2 category when we start looking at shear, okay? Because up until now, one of the things we haven't discussed are these stirrups that go along the beam. Well, stirrup design and shear design is its own sort of unique snowflake. And that's going to be sort of where our exam 2 material starts. After shear, we'll get into, we've done moment, we've done shear, then we do deflections. So, and then you can see the path moving forward. That's all I got, guys. Happy Valentine's Day.
Hey, Dr. Miles, can you tell me the last page?
Yeah. Hold on. I got to get back to where I was on the slides. The way it saves. All right.